Building an efficient local area network requires a deep understanding of how data moves across physical hardware. When scaling an infrastructure, choosing the wrong interconnectivity device introduces severe performance bottlenecks. To resolve this, we must examine how a network hub and a standard Layer 2 switch handle data transport.
A network hub operates strictly at the physical layer of the OSI model, functioning as a basic multi-port signal repeater. To understand its core limitation, imagine its internal architecture as a simple shared electrical bus. The hub lacks any processing intelligence. It cannot read MAC addresses or analyze data frame headers. When a connected node transmits a bit stream into an ingress port, the hub's internal circuitry simply amplifies that electrical voltage and blindly clones it out across all other available ports. Because every device shares this identical electrical path, the entire chassis forms one large, undivided collision domain. If two nodes attempt to transmit data at the exact same moment, their electrical signals collide on the wire, corrupting the data completely. To manage this chaotic environment, devices are forced to run in half-duplex mode and rely on the CSMA CD protocol to listen for silence before speaking. This creates an inefficient architecture where bandwidth is deeply wasted.
To overcome this architectural limitation, the secondary standard introduces the Layer 2 network switch, which replaces blind repetition with logical routing intelligence. Unlike a hub, a switch operates at the data link layer, allowing it to parse and understand the structural boundaries of incoming Ethernet frames. When a frame arrives at a switch port, the internal ASIC chips immediately extract the source MAC address and log it into a dynamic database known as the CAM table, mapping that specific identity to that exact physical port. Simultaneously, the switch inspects the destination MAC address. If it finds a match within its map, it establishes an instantaneous isolated virtual circuit through its internal switching fabric, forwarding the frame directly to the intended recipient port only. Other nodes remain completely undisturbed. If the destination is unknown, it safely floods the frame to locate it. This targeted delivery breaks the hardware into per-port collision domains, allowing every device to transmit and receive simultaneously in full duplex without any risk of interference.
Now that both operational frameworks are defined, we must evaluate their performance under stress conditions, where a systematic benchmark exposes their stark behavioral divergence. When a network experiences a sudden spike in traffic, a hub-based infrastructure collapses under the weight of exponential collisions. Devices waste critical processing cycles running back-off algorithms, waiting for the shared wire to clear, which heavily degrades real-world throughput and spikes latency. A switch-based architecture handles this stress gracefully. By leveraging internal memory buffers, a switch can queue frames on individual ports if multiple devices attempt to communicate with the same server simultaneously, preventing data loss. Furthermore, from a security posture, the hub creates a dangerous environment where any connected machine can sniff every single packet traversing the network. The switch safeguards this data path by restricting unicast frames strictly to their legitimate physical endpoints. This microsegmentation optimizes bandwidth allocation, eliminates collision overhead, and ensures stable, predictable network convergence under the most demanding enterprise workloads.
Ultimately, switching architecture is mandatory to eliminate collision overhead and guarantee deterministic network performance. When deploying high-performance storage networks, do you prefer cut-through switching for ultra-low latency or store and forward for maximum frame integrity? Leave your technical reasoning in the comments below and subscribe to execute the next protocol.